Today we are going to talk about corrosion of embedded metal. In the previous lectures, we looked at the significance of corrosion and fundamentals of corrosion. Basically, we looked at the corrosion circuit, and then we also, in the second lecture, we looked at carbonation-induced corrosion and the chloride-induced corrosion mechanisms in concrete structures. And now today we are going to talk about bare steel, what are the different type of steel reinforcement available, and we will have one lecture on bare steel which we will cover today, and in the next lecture we will talk about coated steel and non-metallic rebars. And so let's look at the bare steel. Before getting into the different steel reinforcement types, first of all, let's look at why do we need to ensure that these construction materials, or for example steel, is of good quality in steel and concrete. The main reason is most of the structural failure happen due to material deterioration. If you're talking about long-term deterioration process and then structures lead to some failure, mainly we have seen that it is mainly due to material deterioration. As you can see here, it's mainly about 40%, based on the case studies, we found 40%, about 40% failures is mainly due to the materials not being able to meet the adequate properties. And so, if we want to enhance the service life or avoid such failures, we have to make sure that both the steel and the concrete, if you are talking about deterioration, which is basically the chemical attack or long-term degradation process, so we have to make sure that the steel which we use is of good quality, and at the same time the concrete, not just the concrete but mainly the cover concrete, which is actually protecting the steel reinforcement, that also have to be very highly resistant against the deleterious elements. So both these have to be looked at, and there should be a balanced approach. In this module we are going to focus mainly on the steel reinforcement. Now let's look at different type of grades of steel rebars available in the country. Earlier we used to use Fe250, but then there was a demand for higher strength, so higher yield strength, so we went on increasing. Even today people are thinking about Fe700 type or grade steel. So here you can see that the different grades, Fe600, Fe500, 415, 250, all this, how the stress strain behavior of these materials. So generally you can see that as the yield strength is decreasing, the ductility, or the end of the graph actually is moving towards the left, or in other words the ductility of the rebar is actually reducing as we go for higher and higher strength. And if you look at the modulus of elasticity, you see that pretty much still all the steels have similar modulus of elasticity, so that is maintained. But definitely ductility is a problem, especially when we talk about durable structure, talk about earthquake resistant structures. Ductility is very, very important. So the structural system, when we talk about steel concrete system, should be still ductile enough. So the structural engineers have to take care of that part. And why I was mentioning here is this higher grade. When we go for higher grade steel, we should not make ad hoc changes at the site, by reducing the number of steel rebars and increasing the grade of the steel. We should leave it to the structural engineers or designers to approve. Then only we should go for higher grade steels, otherwise it might affect the ductility of the structural system. Now let's look at the influence of different chemical ingredients, or what the chemical composition of the steel on how they are actually influencing the various properties. Let's say very briefly we'll go through carbon. It influences the hardness, strength, and weldability, brittleness. All these properties will get influenced if you change the carbon content. For example, here you can see if the carbon content is more than 0.3%, then the steel might become unweldable or it might become very brittle in nature. And then manganese, it influences the yield strength. Sulfur, it influences the brittleness. And then phosphorus influences the strength and brittleness. Also corrosion. Also the phosphorus influences the corrosion properties also. Then the copper, also it influences the strength and corrosion resistance. Chromium influences the weldability and corrosion resistance. Then carbon equivalence, it affects the hardness, tensile strength, and weld. So all these properties which are very much important for the good performance of the structural system, these need to be looked at. Even though some of these elements are in very, very small quantity in the steel, they are still very important to be considered. Otherwise you will see that the steel which you use is having very different properties than expected. Now let's look at different type of rebars which we are going to cover in this module. First one is plain or hot rolled mild steel rebars, and then next one is cold twisted rebars. Then we use thermomechanically treated, or scientifically speaking, it is quenched and self-tempered steel. It's QST steel rebars, but in India we call this as TMT. And then we also have CRS rebars, which is corrosion resistant steel. And then we have stainless steel rebars and prestressing steel strands. So until here we will cover today in this lecture, and then we will move on to coated reinforcing systems. So let's look at plain and ribbed or hot rolled mild steel rebars. So these are the first type of hot rolled bars which were in use in the industry, mainly after the flat or strip reinforcement which were used in the first generation concrete structures. Then there was a need for more resistant steel and higher strength. So let's look at the plain and ribbed mild steel rebars, mainly hot rolled steel. So in the plain rebars, these are the first type of hot rolled rebars. Mainly, initially the flat or strip type reinforcement were used, and then the industry started using this, round shaped rebars, and these are actually more resistant to corrosion than the cold rolled steels, because the energy level is less of this type of steel. And then but not very much used in today's construction. Mainly today we are talking about high strength elements, and the demand for high strength materials are there, so we are not using plain or mild steel rebars much. So let's look at the first type of rebar discussed in the previous slide, which is plain and ribbed mild steel bars. These are mainly hot rolled steel, and these were used in the very beginning, just after the flat or strip reinforcement came into the market. And then this type of rebar are more resistant to corrosion than the cold rolled steel, because when the process is hot rolled, the energy level of the final product is little less than the cold rolled steels. And then you have also there was a demand for higher strength steel. So nowadays we don't use this type of plain bars much, and also there was a requirement for better bond between the steel and the concrete. So people started using the ribbed bars, which is, you can see that because of these ribs over here, it enhances the friction between the steel and concrete. So you will see that it is the deformed bars are used in the market, especially for the primary reinforcement. In the shear stirrups, you might still see in some places where the plain bars are used. The other type of rebars which were in the market earlier is cold twisted deformed bars, because there was a demand for a higher strength without really changing the chemical composition. So industry went on with cold working the steel, or these are basically cold worked steel or work hardened steel. This cold here doesn't mean the cold which we feel, but it's basically a temperature at which below the recrystallization temperature, they twist the rebar, as you can see in the image here. Just like after taking bath, we twist the cloth or the towel. So just like that, these rebars are twisted rebars. So you can see the ribs are going something like this, and not like what you usually see in today's steel, which is available in today's market. So these are the ribs, and these are this long, I call it seam, like in a cricket ball. You can see this portion here, and it is twisted bar. Okay, so this is twisted like this. So you can very clearly see how the bar is twisted, but this twisting process leads to some residual stress on the surface of the steel, because of which it is more vulnerable to corrosion. Because of this residual stress, this surface has higher energy level, and that will lead to a more vulnerable steel surface. So if you look at the microstructure, how this called cold working process and what it does to the microstructure. So before the rolling, you can see here in this picture, all these grains have similar size in both the x and y direction, or the horizontal and vertical direction in this picture. Whereas in the second image here, after rolling, the rolling direction is in this way. The second image, you can see that these grains are elongated in parallel to the rolling direction. So this tends to leads to a higher energy level, and the bars will tend to corrode faster. The other type of, and so before we go to the other type, so because of this, nowadays it is not really used in today's construction. And so the industry went on to another solution, which is thermomechanically treated steel, where again the the chemical composition is not much changed, but the manufacturing process is changed a little bit. And what you can see is, look at this graph here. In the manufacturing process of this type of steel, initially the temperature is around 1000 degrees Celsius, and within 1 second, this is in a log scale, the horizontal axis is in log scale here. In about 1 second, because of the quenching process, the steel surface temperature reaches about 200 degrees. That's about 800 degree reduction in about 1 second, in 1 to 2 seconds you can say. And then at that moment, the core of the steel is still really hot. So the core temperature is this curve here indicate the core temperature, and this curve here indicate the surface temperature. So the heat from the core is radiating outward, and it tempers the surface which is quenched. So that's why we are calling this quenched and self-tempered steel. So in other words, we are tempering it because of the heat which is radiating outward from the core of the steel. So this is the correct term for this TMT rebars, but in India we have, in Indian jargon we call it TMT steel. What are the advantages of this TMT steel? The main advantage is it's very ductile in nature, mainly because this center portion here, or the core of the steel, is ductile in nature, whereas this the peripheral region, which is tempered martensite, it contributes to the strength and hardness, or the surface hardness, it contributes to that. So because of this large area covered by this ferrite perlite, which is more ductile, you get, really it is possible to get about 18 to 30% elongation, which is very much necessary for building earthquake resistant structures. Now most of the time we have seen that in some type of rebars available in the market, this composite nature or the cross section of the rebars are not as it is shown on the picture here. You have to have this core which is ferrite perlite, this region ferrite perlite, and you also have to have a peripheral tempered martensite region. Then only you will get highly ductile, with good surface hardness and sufficiently strong steel. And ideally, this is the 20 to 30% of the cross section area should be having this tempered martensite phase. But we are seeing that there is a huge variation in these things, which leads to a variation in the mechanical properties of the steel. Also, we recently, we observed that there is a need to test the rebars at the site and make sure that these are actually having this kind of cross section. We have developed a test which we are calling TM ring test. TM stands for tempered martensite ring test. I will go through that test a little bit later. So this is how the test setup is. On the right side, what you see is the test setup, where at the bottom over here you see a small test specimen. On the left side you see the test specimen that is kept here on the bottom of this camera. And if you have a proper lighting, and you can cut the steel cross section and then etch the steel surface using a 5% NPTEL solution. It's a very simple test, hardly takes about 5 minutes to get the test results. So you cut the steel surface, and then I'll show a video later to cut the steel surface and then etch it by using 5% NPTEL solution, and then you will get you'll see that the steel will start reacting with the acid, and then it will form these two different colors on the surface. So you can see this video here. On the left side is a poor quality rebar specimen. On the right side it is a good quality rebar specimen. So you can see now we have placed this NPTEL solution, which is basically nitric acid in ethanol, not in water, in ethanol. So 5% NPTEL solution. You can see on the left side there are proper ring is not being formed, whereas on the right side you have a very good ring formed. So very clear, the right side rebar is actually better manufactured, or the quenching process and the temperature, self-tempering process, that is better controlled in the right side steel on the right side. So this is what you see on the right side is what we really need to have. But there are many products in the market where you see only very inadequate ring. So this is an example of the case A here is a good rebar. It's very good. This case B, this is not good, not good, not good, because you can see where these red dots are placed. This region you have very little tempered martensitic phase. Here also there is a disconnectivity. This is disconnected, this is disconnected, so this leads to earlier corrosion, or it can lead to corrosion at a lower chloride concentration. So we definitely have to prevent the use of such type of steel. So I request if it is we must actually do this test and ensure that the TMT steel is having this composite nature like what is on this first picture here. Like a proper ring is necessary. This is a market results from a market survey where we did some testing. One thing to notice here is, as the diameter is smaller, you see that there are more rebars, or more, these A, B, C, D, E's are the different products which we found. As the diameter is smaller, you can see that these kind of problems are much more in the smaller diameter rebars. So all these are not really good type rebars. Whereas in the larger diameter bars, only one case over here we found some problem. Now we can, if we do this test, why I showed this slide is to make sure that the test is done on all the diameters, or the rebars, all the different diameters, because you cannot just grade or the rate the product based on a TM ring test on a larger diameter rebar, because in this case B, you can see the 16 mm diameter bar is okay, but the 12 mm diameter bar, it's not okay, because you have a very thin tempered martensite over here. So like this, you can see very thin tempered martensitic region. So that's not good. As you reduce the diameter to 8, it is really bad steel. So what is the impact of this? Why I am saying this is not good? The impact is this. On the left side is an image. You can see at the bottom of the screen, on bottom left, you can see a cross section, very good steel. When you bend that, there is no crack in this region. It is perfectly all right. There is no crack induced due to the bending. But on the right side image, you can see here, this is the how the cross section is. Here also very little. It is not uniform. And when you bend this, it leads to significant cracking. You can see all this region, it's several cracks here. So this is the problem when you talk about or when you use this kind of rebars with inadequate tempered martensitic face or inadequate cross section. Now why, again I am saying, what is the issue with this crack or where you can see this crack? First of all, we are using this tempered TMT steel mainly because you want ductility and you want earthquake resistance. So when you talk about earthquake resistant design, you have to have a requirement most of the time. The stirrups, we bend it by 135 degrees, not just 90-degree bend. Like shown in this picture here, you can see here, this is bent by 135 degree as it is shown in the sketch over here, the diagram. Now, when these bars are prone to cracking, where it will crack right here, right where that bending is happening or at that bend region, and outside portion of the bend surface, outside surface of the bend, it will crack. And now if you have a crack like this, this will tend to corrode even with very, very low quantity of or low concentration of chlorides, because the mechanism is slightly different. Sometimes we can call it as a crevice type of corrosion will happen at these locations because of the crack, the presence of the crack. So if I go back to the previous slide here, what will happen is, if I have a crack like this, so chlorides can enter through this, go into this crack and then stay there, and then it will start corroding deeper and deeper right here. So it will some kind of crevice corrosion can happen. So that is the danger. And one more thing to mention here is, when we talk about the stirrups, shear stirrups, these are the bars which with the shear stirrups will have smaller cover than like imagine this, in this case, imagine this is the concrete surface, and now this shear stirrups have only the cover is only this much, whereas the primary reinforcement has a larger cover than what is available for the shear stirrups. Now if the shear stirrups are cracked, and you will see that will corrode before the primary reinforcement. So if you look at any structure which is corroded, you might most often see that these shear stirrups, and that too at the bend portion, are the region which are corroding. So then it compromises the structural capacity. So point here is, we must do a bend test on the TMT steel and also do this TM ring test. So bend test plus TM ring test. So these two things we must do in addition to all the tensile strength test. Otherwise we might be actually compromising the corrosion resistance of the steel. Now we also have this corrosion resistant steel or CRS rebars in the market. Mainly these are the rebars with the difference in the chemical composition. Mainly they have small quantities of copper and chromium is present, and also slightly higher quantity of phosphorus. This is the main difference in the CRS steel when compared to other type of steel. Now people say that the CRS steel is highly corrosion resistant. I mean, the name itself claims so, but when you talk about the service life, it is not the corrosion rate which is the key factor, which because of, it is an important thing, but important parameter, but additionally we must ensure that the chloride threshold or the amount of chlorides required to initiate the corrosion. Because when you talk about the service life, the initiation phase is the one which really governs the life of the structure. So what we should have is a steel which has a higher chloride threshold than a steel which has a lower corrosion rate. If you really look at these two and look at the impact of them on the service life, we must test the chloride threshold of CRS steel in addition to the corrosion rate. I am not saying not to test the corrosion rate, but the decision should be mainly based on the chloride threshold and its impact on the service life, which is not usually done. I mean, this chloride threshold, people generally test only the corrosion rate and make decisions. So we must test chloride threshold. That's the key thing, which is the amount of chloride required to initiate the corrosion. So now let us look at the stainless steel. What is stainless steel? Mainly you have steel with more than 11% chromium plus nickel plus molybdenum. So this enhances the resistance of the this type of steel, mainly by having a passive film which is rich in chromium oxide passive film. And the picture here very clearly says the advantage, or depicts the advantage of the stainless steel. On the left side, what you see is these pillars, which were built about 30 years after building this structure, which is made of stainless steel. So this bridge on the right side is still standing without any corrosion issues. So definitely the money you spend, because definitely stainless steel costs about 6 to 7 times more than the regular or conventional reinforcement, but still there is an advantage of using this. So point is, if you have enough money, budgetary constraints are not there, and you want long life with minimal repair, then definitely stainless steel is a very good option to go for, provided financial constraints are not there. There's a couple of other examples where in New Jersey and in Canada, Toronto, Canada, where examples of bridges with stainless steel rebars. So it's not that people do not practice this. They practice this because they know very clearly that if they go for the other type of rebar, there will be huge repair activities or the need for very frequent repair. So in such cases, we really may have to go for highly corrosion resistant steel. One of them is stainless steel. Now, in India now there is a trend to use combinations of stainless steel and other steel rebars in some structural elements, because stainless steel is very costly. They think can I use stainless steel in some portion of the structure and the other type of rebar in other portion of the structure, so that the project cost is still not it doesn't increase significantly. But when we practice this, the mix of two type of steels, we must check the possibility of galvanic corrosion between the two type, between the conventional steel rebar and the stainless steel rebar. And if the impact of this galvanic corrosion on the desired service life, not just the immediate future, but if something is designed for 100 years, this galvanic corrosion should not lead to any significant problem and for that time period. So that must be checked. So the galvanic current should be so low that even after 100 years there is no significant problem. That must be checked before recommending such combinations. Now, prestressing steel strands is another type of steel which we are using very much in different type of structures today. Railway sleepers or railroad ties, this concrete sleepers, and then very tall electric poles or mast. You can see here, when you go for very tall, then the lateral resistance is so high, the loads are so high, and then you really need to go for pre-stressed concrete, otherwise the structure will be very bulky. And large span bridges, long span bridges, and the type of how these steel strands come into the market, mostly they come in as a coil, because you're talking about using these things in very long spans. So small rebars of 10 meter long is not enough, so it comes in coil. And Also, nowadays we use this type of strands in high-rise buildings also, where uncoated strands are also used, but also there are products which are sheathed strands. For mono strand, I mean, this comes in single units. So you can see over here, when you talk about this in high-rise buildings, if the post-tension slabs are, post-tension slabs, they use this kind of mono strands very much, because you don't want to bunch a lot of strands which will lead to significant bursting stress. So they distribute the positioning of these strands, for which mono strands are used. And now in some new project, we even started using fusion bonded epoxy coated strand. I would say we should be very careful when we use epoxy coated strand. More details I'll cover in the next lecture, but there should not be any scratch on this epoxy coating, and they should not be exposed to ultraviolet radiation or sunlight for that matter. Otherwise, you might see that this coating will degrade, and if there is scratches, it will not serve the purpose for which they are designed for. So when you use coated rebars, we have to be very careful in handling them very delicately, so that mechanical damage and UV induced degradation is avoided. So where we use this high strength steel materials, so in metro rails, elevated highways and flyovers, then bridges or long span bridges, power plant, any large structure, when you talk even high-rise buildings, we use heavily all these different type of steel rebars and strands and cables. So on the this bridge here, these are basically the type of cables on the bottom right corner. So different type of cables are used. So go from single solid rebar or wire depending on the diameter, and then multi-wire strands, and then you have multi-layered cables. And so these are different type of steel reinforcement when you talk about very high strength requirements. Now in the pre-stressing steel, it's a cold drawn steel, not like the mild steel which is hot rolled. And in the cold drawing, what is happening with this cold drawing is, you see the picture on the left, which is a microstructure, which shows the microstructure before the cold drawing process. And on the right side, you can very clearly see all these faces are aligned in the direction of drawing or rolling direction. You can see these are all kind of vertically aligned over here, and that actually induces some pattern of corrosion in the steel also. So you can see a pyritic structure with a matrix of ferrite with plates of cementite. So parallel lamellar structure you can see in this after cold drawing. So there is a rearrangement of the faces. Now ultimate strength of this type of pre-stressing steel is about 4 to 5 times more than that of typical reinforcing steel. Also the yield strength is also at similar 4 to 5 times yield strength is also expected, depending on what your base steel is. Now how the corrosion phenomenon in this type of steel, I'll cover separately one full lecture on what are the different type of corrosion mechanism in pre-stressed concrete. But very briefly, let us look at this. On our first picture here, the top one is a deformed bar or the typical conventional reinforcement. The bottom bar, this one is a steel strand. So this is a conventional thing, and this is a steel pre-stressing strand. And the close-up image is shown here, where you can see that there is a severe pitting happening locally, not everywhere, but very locally. As in the case of the conventional reinforcement, you can see that the number of locations of pit is much more, or it's spread more along the surface of the steel when as compared to that is happening on the prestressing steel. So this localized corrosion is very dangerous, because the prestressing steel is under stress all the time, and because of the stress there may be some micro cracking, and which is leading to this localized corrosion. Now to summarize, we looked at the balanced approach necessary to enhance the quality of the steel concrete system. We have to work on the quality of both steel and concrete, and then demand for higher strength and better corrosion resistance led to different type of steel rebars which are now available in the market. From mild steel we went to CTD, and then we went to TMT steel. Now we are talking about stainless steel, prestressing steel. So different type of steels are available to cater to different requirements of various structural elements. CTD bars are no longer in use because of its relatively poor corrosion resistance. Now better quality control of TMT steel is essential. Lot of products are available in the market, but when we really look at the cross section or the composite structure of the TMT steel, we find there are many products are not meeting the requirement of having a very good TM or tempered martensite ring, recommending the TM ring test to do in addition to the tensile strength test or mechanical tests on mechanical characteristics. And also we must do bending test when you talk about TMT steel, because bending and then look at whether it is really cracking or not. If it is cracking, we should not use that, because that will lead, such cracks will lead to corrosion at much lower chloride content, mainly because of crevice corrosion phenomenon. And also chloride threshold is a very important parameter, especially when you talk about CRS or any steel for that matter. Chloride threshold should be looked at in addition to the corrosion rate, because chloride threshold really governs, chloride threshold and the diffusion coefficient of the concrete really governs the service life of the structure. And stainless steel offers good resistance, but of course the combination of stainless steel and other steel is in practice today to reduce the expenses, but that must be allowed only if the galvanic corrosion is minimal for the desired service life. And prestressing steel, they can be prone to deep pitting corrosion or localized corrosion because of the high stress they are experiencing as compared to conventional steel. So all these must be looked at when we talk about steel. In the next lecture, we will talk about how what are the different type of coated reinforcement which we have in the market, both metallic and non-metallic coating we will look at. And these are the list of references. If you want to read more about this, you can please go through these references. Thank you.